In this video, we're going to introduce a new measure of how effective an amplifier is at making a signal bigger, called power gain. Power gain is relevant because we care about how power flows through S-parameter networks, especially amplifiers. But we're going to skip the S-parameters in this video so that we can get a sense of how power flows without having to worry about complex math. We'll add S-parameters to our power gain analysis in a future video. One of the first things to discuss is the need for power gains at all. You've used amplifiers before, and we've mostly thought of a voltage source driving them, and the amplifier providing some voltage gain to that voltage source. For instance, this is probably how you learned to think about op-amps. And voltage gains seem to work great up until now. So why abandon them? Well, one argument against voltage gains is that we've been examining how convenient it is to do math with power. That math lets us avoid thinking about complex exponentials, and it lets us compare signals of very different power levels using logs. And that argument still holds water. But this first model also hides some details, so we need a more detailed model. Our first model presumes that the input impedance of the amplifier is really high, so that the amplifier doesn't load the voltage source. That doesn't work at RF because terminating a transmission line on an open will result in reflections, and reflections make designs complicated in a lot of ways. For instance, you have to care about the length of your cable. Instead, we usually want our source impedance and our input impedance to both match our line, which means dealing with the relatively low impedance level of 50 ohms. We have the same problem at our output. Our out and our L are probably pretty close to Z0. Since we've matched our cables, we know that eventually all our voltages will settle to levels that are consistent with a circuit where the cables don't exist. So we can find a loaded Vout over Vin using voltage dividers. And this loaded voltage gain is smaller than the amplifier's voltage gain of A. So we'd like to make sure that our metric for gain takes source and load impedances into account somehow. But your next question might be, why isn't loaded voltage gain a good enough metric? Why go to power? And there are several reasons. As I mentioned above, power gain is convenient for many analyses because we can simplify our analysis by thinking about gain magnitudes and discard phase information. Power gain is also useful when the input and output have very different impedance levels. And finally, power gain lets you capture information about gain even when your signals are currents and your gains are current gains. So it's a universal language for a lot of type of circuits. And that's particularly important because voltages and voltage gains are often small at high frequencies, which makes them hard to measure. However, we're going to hit a sticking point almost immediately as we try to calculate power gain. There are lots of ways we can define power. I've shown 4 options on this slide. The power pulled from the source, the power available from the source if the amplifier input is matched, the power delivered to the load, and the power delivered to the load if the output was load matched. You might notice that I've omitted the transmission lines from the schematic on this slide, and that's fine because we decided to match our source and load to our lines on the last slide. So the driving point of the impedance of the line is equal to the source or load impedance. Let's calculate these gains. The first is power from the source. This is the power that came out of the source and makes it into our amplifier. It's given by the voltage on Rn squared divided by Rn. The voltage across Rn is set by a voltage divider attached to Vn, so we get a big squared ratio in this expression right here. And note, you could measure this value by measuring V1 and Vn, even if you didn't know Rn exactly. We'll also consider the power available from the source, which is the power that would come out of a source and into the amplifier in the best case scenario where the amplifier is source matched. We know that a matching impedance is the best case scenario because of the max power transfer theorem. Since we know that Rs and Rn are the same in this case, we know the voltage on Rn is Vn over 2. So squaring appropriately shows this is Vn squared times a quarter. This is exactly half the power delivered from Vs, again by the max power transfer theorem. We need to compare source power to power dissipated in the load, which is given by the voltage across the load squared divided by RL. And we can relate this voltage back to, so that's there. We can relate this voltage back to Rn by tracing back through a bunch of dividers and applying the amplifier gain. And then finally applying the input divider. Squaring all of these gains and dividers gives a sprawling expression for the load power. So this is kind of big. Finally, the power available to the load is the best case power delivered to the load when Rout is matched to RL. As with the power available from the source, half of the power comes out of the amplifier, winds up in the load in this case. The equations I show here track some dividers back through the circuit to show a relationship between the load power quantity and Vin. That quantity depends on the Rs to Rin divider. Because we only assume the load is matched, the source could be mismatched when we calculate this available to the load power. Now that we have some interesting powers, which I've copied over from the last page, we can think about taking ratios of them to make gains. The first power gain is probably the most intuitive. Power into the load divided by power from the source, and that's called power gain, or GP, or sometimes operating power gain. The expression for this is easy to find by comparing the PL and PS expressions. We're looking here and here, and looking for terms that knock out. So Vn squared falls out, and the Rn here and the RL there become a ratio, and this input mismatch term falls out of both of them. I've included a brief sentence describing power gain in words to try to make it easier to apply in practice. This gain is the ratio of power into the load to power that makes it into the amplifier. Consequently, this gain doesn't account for output power that we're leaving on the table by not matching the input. On the upside, it's pretty easy to measure by finding V1 and Vout. The second power gain we care about is called the transducer gain, GT, and it attempts to rectify some of the issues with GP. The expression again comes from a ratio of powers on the page, and because PAVS assumes an ideal match while PL does not, none of the divider terms cancel. So describing this gain in words, it's the power into the load assuming the input is source matched. Or you could say that it's the power in the load divided by the best possible power we could get from the source. Comparing against a power that assumes a perfect input match makes GT more pessimistic than GP. It's affected by the quality of both the input match to see if the real system input power lives up to PAVS, and by the output match. And that's because that's baked into PAVL. So this term comes from PVA, isn't canceled because we're using PVAVS, and this is part of the load power. This is the most common gain reported for our systems, RF systems, because it cares about both input and output matching. Finally, we'd sometimes like to know the best power gain we could achieve, which is called the available power gain, or GA. This expression may be a bit surprising. This expression may be a bit surprising because of the Rs to Rn divider that appears in PAVL. But this gain, unlike GT, assumes matching at the input and output for both numerator and denominator. Consequently, the Rs to Rn divider just turns into a factor of 1/4. So, said in words, this is the power into the load, assuming both source and load are matched, divided by the power into the input, assuming the source is matched. This is mostly nice as a handy upper bound on amplifier performance. So, last slide was that we spent a lot of time talking about how different types of power gains accounted for different types of matching. So perhaps it's unsurprising that all of these gains assume the same value if your system is matched at the input and the output. So if we assume that Rs is equal to Rin and Rout is equal to RL, we find that both GP and GT assume the same value that GA had all along. Each of the divider ratios becomes 1/2, and squaring those yields a quarter. And the 4 in GT cancels out with one of those factors. So the end result is that we achieve the available power gain by matching the input and the output. So, in summary, power gain is important because it accounts for impedances of sources and loads. We care about 4 powers: the power from the source, the power available from the source if the input is matched, the power to the load, and the power available to the load if the output is matched. And we care about 3 types of power gains. There's operating power gain, or just plain power gain, which assumes no matching, and the input mismatch cancels in the numerator and denominator. That's a little optimistic because it ignores input mismatch, so we also care about transducer gain, which assumes a perfect input match, resulting in kind of no cancellation of your mismatched terms. And finally, we care about available power gain, where all our terms cancel and we have just a best case scenario. And all power gains are the same if the input and the output are matched. We achieve our available gain by matching the input and the output.